Justin Miller, Oxford College Physics here. We are going to do some problems with standing waves on strings and air columns. So let's just get to it, shall we? Start looking at standing wave on the string fixed at both ends. So here's the problem. All right, so we've got ourselves a string that has some length and has a linear mass density mu of 80 grams per meter. We have that it has waves that travel across it with a wave speed of 45 meters per second. So there's the wave speed, and we're told that we are oscillating the string at a frequency of 20 hertz, which produces an n equals 5 standing wave. So we'll call this f sub 5 is equal to 20 hertz. And we are asked in part A, what's the tension in the string? That's pretty easy to figure out. And then part B, what's the length of the string? And then we start asking some more nice questions about things. All right, so tension in the string. Well, we know that tension in the string is related to the wave speed and the linear mass density by the expression of the square root of T over mu, so that the tension is going to be equal to mu times V squared, which is, be careful of this is in grams per meter. We want in kilograms per meter so that our tension is in newtons. So we've got 0.08 kilograms per meter multiplied by 45 meters per second quantity squared, which gives us a whopping 0.08 times 45 squared. 162 newtons. Fantastic, we got a pretty tense string there, tension in it. Let me go ahead and transition over to part B. How are we going to figure out what the length of the string is? What does that correlate with? Well, it correlates with the harmonic number, or the order number of the standing wave, the frequency of the standing wave, and the wave speed of the standing wave, right? We've got this in general, that F sub n is equal to NV over 2L for waves on the string that's fixed at both ends. So that's our go-to with this. We know what V is, 45 meters per second. We know what N is, it's going to be 5 for F sub n. And we've got then this. F sub 5 is equal to 5V over 2L. We can solve this out for L and get ourselves that L is then equal to 5V over 2F sub 5. And what is this going to give us? There's a couple of things that we can actually mess around with. I'll show you that in a minute though. We just put in our quantities here. We've got 5 times 45 meters per second divided by 2 times 20 hertz. And just stick this in here. 45 times 5 divided by 40. 5.625. 5.625 meters is the length of this string. And that's a pretty long string, right? So we're looking at something like 16, 17, 18 feet or something. Ooh, pretty long string, but that's it. We've got 5 independent loops. So if we kind of looked at this, what does this look like? We'd have 1, 2, 3, 4, 5. Stop. This would be it. We'd have antinode, 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 fixed end, fixed end. 5 separate sections oscillating up and down for our n equals 5 standing wave. Constrained to a string fixed at both ends. That's what it looked like. Each one of these loops just oscillates up and down. When that one's up, this one's down. These are going like this, and like this, and like this, and like this. Anyways, that's what we've got. So we move on. Going over to a part C, we want to know, what is f sub 7? What frequency do we need to oscillate this string at in order to produce an n equals 7 standing wave, or to produce the 7th harmonic. In other words, so what do we know about this? Well, we're not changing the wave speed, we're not changing the tension, the length, or anything, so we're assuming that the length, the tension, the linear mass density stay the same. We just want to oscillate at a different rate. So we know that f sub 7 is equal to, let's just do it like this, 7 times f sub 1. So if we can figure out what f sub 1 is, we just multiply it by 7, right? So we've got this. The f sub 5 is equal to 5 times f sub 1. We know what f sub 5 is. F sub 5 was 20 hertz. 20 hertz divided by 5 is then equal to f sub 1, the fundamental frequency, which is then equal to 4 hertz, which then gives us that f sub 7 is equal to 7 times 4 hertz, which is then 28 hertz. Pretty straightforward there. Go back to the fundamental frequency, note that everything's integer multiples of it. So now we want to do something a little bit different. We want to change this n equals 5 into an n equals 7 wave, but not, an n equals 7 wave into an n equals 5 wave, but not by changing the frequency, by changing the length. So this one, we are going to take ourselves this n equals 7 wave, which is this one right here, and we are going to change the length of the string that's constraining it. We're not going to change the wave speed, we're not going to change the linear mass density, so we're going to keep the same tension in it. We're just going to change the length of the string such that an n equals 5 wave is constrained to it. So what does the new length of the string have to be? All right, so now we want f sub 5 to be equal to 28 hertz. That's what we want. What must the new length be equal to? Well, we just go back. Go back to the fact that f sub 5 is equal to 5v over 2l. And we get a new length, right? The length will be equal to 5v over 2f. 5v over 2 f sub 5. What's changed? F sub 5 is 28 hertz now. We still got the same wave speed and all of that good stuff. So we've got 5 times 45 divided by 2 times 28. 656. And we want to change the length down to about 4.018. 4.018 meters is what we want to change it down to. There we go. Such that F7 changes into an F5. And we can start changing this with respect to time and looking at all sorts of characteristic dynamics that occur. But anyways, just looking again at correlations between length. We oscillate at specific frequencies. We can start playing around with the length to produce certain effects, or we can change the frequencies. We can give them length to produce certain effects. All sorts of good stuff like that. All right, so let us move on and do another problem here. We've got ourselves a problem where we want to look at air columns now. So here's the problem. All right, so we've got ourselves an air column that is open, closed, and that produces a fundamental frequency of 262 hertz, which is approximately middle C, C4. So we've got that the fundamental frequency, we're told, is 262 hertz, open, closed. And we've got that this has to have a certain length. And indeed, we want to know what is the length that is required for this open closed system to produce that particular frequency of C4. So what we got to be aware of is two real things here. Number one, open closed system. We've got the frequencies, f sub n for an open closed system are nv over 4L, where n can only be odd. All right, so with this we should be able to figure out the length pretty easy. What's the other thing you ask? Well, the other thing that is v is equal to the speed of sound in air. We'll assume that we're in air. If we're not given the temperature, what's the speed of sound in air? I'm going to say it's 343 meters per second. If we're told that the temperature is something other than 20 degrees Celsius, then we've got to go ahead and figure out what the wave speed is. But this is something that gets messed up commonly, is people forgetting that, hey, if we're talking about air columns, this V here is the speed of sound in air. So don't forget that. I'll even subscript it here with V sub air. Even though we don't usually do that, let's put it there explicitly. So what do we get out of this? Well, we've got that f sub 1 is going to be V over 4L, and thus L is going to be equal to V over 4 f sub 1. F sub 1, 262 hertz, V is 343 meters per second, so we get ourselves that L is equal to 343 meters per second divided by 4 times 262 hertz. And how long does this air column need to be? Ooh, let's see, it's not too long. 43 divided by 4 times 262. About almost 33 centimeters, we'll say 0.3273 meters, or 32.73 centimeters. So what is that? Well, we come out with the meter stick. That's not that long. That's somewhere around like that from the end of my finger. It's not too long. It's a little bit longer than this one. This one's a little bit shorter. Open close, so frequency of this is going to be a little higher or a little lower than C4. That's right, shorter, higher frequency. So, anyway, C4 is a little bit lower pitched than that. Regardless, there we go. There is the length for the open closed system. Now, we're told something else. This is a nice part A. Part B. Now we're going to take an open system that has a length of 1.3 times the length of this open closed system. Say, what is the fundamental frequency of this system? So, B, open, where L is equal to 1.35 times, we'll call this L sub OC for open closed. Call this L sub OO for open, L sub OC, which is 1.35 multiplied by 0.3273 meters. So we've got L sub open. It's going to be a little bit longer than that. All right. Let's take that times 1.35 and say that that is going to be 0.4418 meters approximately. We want to know what's the fundamental frequency of this? Well, for open, we've got the fundamental frequency is NV over 2L, where N equals 1. So let me just get rid of that. V over 2L. So what do we do with this? And we got that this is going to be 343 meters per second divided by 2 times the length being 0.4418 meters. And at that, get about 388 hertz. We'll just round it off. 388 hertz, which we could look up on a table of pitch versus frequency and figure out what note that's actually closest to. It's probably in between, something a little sharp, something a little flat. Doesn't matter. 396 is G, so it's a little bit lower than G. Probably B flat, B sharp. Anyways, regardless, we figure it out. There is the fundamental frequency. And again, if we started talking about higher order frequencies, like, hey, what's the frequency of the fifth harmonic that's in the sound? Well, if it's the open-open system, multiply this by 5. It's the open-closed system, we multiply the 262 by 5. Say, hey, that's the fifth harmonic in there. What happens if we say, what's the second harmonic? Well, the open-closed system doesn't have a second harmonic because it only has odd integer multiples of the fundamental frequency, only odd harmonics. While this one, we just double this, and that would be our second harmonic. Anyways, that's what we've got. We could think about changing the length of a tube over time, figuring out how long it takes to get from one frequency to another, or what rate you have to change the length of the tube to produce a certain frequency separation in time. All sorts of little fun problems that you can make out of these. And you'll probably see some on some exams at some point, maybe. All right, at that, that's it. Have a good one. Be well.